We've developed the machinery to solve the time-independent Schrödinger equation for the delta function potential by connecting solutions covering the regions away from the delta function and matching them together with boundary conditions at the delta function itself. The last lecture discussed the bound state solution. This lecture discusses the scattering state solutions. To put this in context, what we're talking about is a potential v of x given in terms of a Dirac delta function. A now is just a constant that defines how strong the delta function actually is. So our potential is everywhere 0, except at some point where it goes to negative infinity. This is a plot now of v of x as a function of x. What we discussed in the last lecture was the bound state solution. What happens if we have an energy E of our state that's less than the potential, less than 0, less than the potential away from the delta function? And what we got was a wave function psi of x that looked something like this. Going down towards 0, away from the actual position of the delta function. I haven't done a very good job drawing this, but I think you get the idea. The scattering state solutions, by contrast, have energy greater than 0. So we're talking about solutions with energy E up here. At regions away from the delta function, we have basically the behavior of a free particle. We get traveling waves at regions away from the delta function, away from x equals 0. We don't really know what happens at the origin, but we know what our solutions should look like, and we should be able to use our boundary condition matching to figure out what happens at the origin. So what do our scattering states look like? Well, away from x equals 0, we have v of x is equal to 0. That means our Schrödinger equation, the time-independent Schrödinger equation, looks like minus h bar squared over 2m times the second derivative of psi with respect to x. No potential now is just equal to E times psi, where energy now is strictly greater than 0. We can manipulate our constants, much how we did when we were talking about the bound state, and express this as d squared psi dx squared equals minus k squared psi. Now I'm defining a slightly different k than when I was talking about the bound state solution because we have a different sign for the energy. Instead of having k be a negative or imaginary now, I'm going to again have k be positive and real by saying k is equal to the square root of 2me over h bar. If you recall, when I was talking about the bound state, I had e less than 0 and I had a minus sign inside this expression. Looking at this ordinary differential equation, we can write down the solution. And the solution is, let's say psi is equal to a e to the I kx plus b e to the minus I kx. When we take the second derivative of this exponential, we'll bring down an ik quantity squared, which will give us a minus k squared. Since we're talking only about regions away from the delta function, we really actually have two general solutions here. We have psi 1 for regions for, say, x less than 0, and we have psi 2 for x greater than 0. Psi 2 now, to the right of the delta function, is going to look very similar, and it's going to be f e to the I kx plus g e to the minus I kx. I should write this as a capital G, sorry. Instead of saying c and d, I've jumped ahead to f and g to eliminate any possible ambiguity if we have to assign future constants, for example, e. So, we have our two general solutions covering regions for negative x and for positive x. What happens at the boundary? How do we match these solutions up? Our boundary condition matching, in terms of these two general solutions, is a two-stage process. We have two distinct boundary conditions, and the first is that psi is continuous. What that means is that psi 1 of 0, our solution for negative x, evaluated at the boundary at x equals 0, must be equal to psi 2 of 0, our solution for positive x's evaluated at the boundary. If I substitute 0 in for these exponentials, for x in these exponentials, what I end up with here is reasonably straightforward. A plus b equals f plus g. That's the result of our continuity boundary condition. And it helps, but it doesn't help all that much. We only get a single equation out of this, so we need to do more. The first derivative boundary condition is that the first derivative of psi is continuous, provided that the potential is finite. However, in this case, our potential is given by delta of x, which does not remain finite at x equals 0. The trick that we used when we were discussing the bound state solution was to effectively integrate the Schrödinger equation dx from one side of the boundary, minus epsilon, to the other side of the boundary, plus epsilon. When we integrate this, we should still have an equality, integrating the terms on the left-hand side and integrating the terms on the right-hand side. And knowing the properties of the delta function, we can simplify this integral greatly. I refer you back to the notes for the last lecture to see what this actually works out to be. What it tells you is that d psi dx, the first derivative of psi, which we get from integrating the second derivative of psi, evaluated at epsilon, and then subtracting the value evaluated at minus epsilon, essentially the change in the first derivative as we go from one side of the boundary to the other, is equal to minus 2 times m times a, the strength of our potential, over h bar squared, times psi evaluated at 0. The right-hand side here we actually got from the integral of our delta function times psi. So this is our boundary condition here, appropriate for use with delta function potentials. This tells us about the behavior of the first derivative of psi as we cross the boundary. So we're going to need to know what our first derivatives actually are. Well, psi1 was equal to a e to the ikx plus b e to the minus ikx. So if I take the first derivative of this and evaluate it at effectively 0, some very small quantity, what I'm going to get for d psi1 dx evaluated at 0, essentially, plus or minus epsilon. I'm looking at psi1 now, so I'm talking about the negative half plane, negative x's. What I get is ik is going to come down from both of these, and I'm going to get an a minus b. I can do the same sort of thing for psi2, which was equal to f e to the ikx plus g e to the minus ikx. When I take the first derivative of this, d psi2 dx, and evaluate it at the boundary, I'll end up with ik times f minus g, by similar reasoning. That means the left-hand side here, which I can calculate by looking at the derivative of psi for positive values of x as x goes to 0, this expression, and subtracting the first derivative of psi for negative values of x as x goes to 0, this expression, what I end up with is ik times f minus g minus ik times a minus b. That's the left-hand side now of our expression up here. Our right-hand side is minus 2ma over h bar squared times the value of psi at x equals 0. Now, if you look at either one of these definitions, you can see what happens when we substitute in x equals 0. We get a plus b for this one, or f plus g for this one, and I have a bit of a choice as to which one I want to use. In this case, I'm going to use a plus b, and you'll see why in a moment. What we end up with now, if you manipulate this expression a little bit and define a useful constant, in this case the constant is going to be beta, just to save some writing. Beta is defined to be ma over h bar squared k. What we end up with is f minus g is equal to a 1 plus 2i beta minus b 1 minus 2i beta. And this is the result of our first derivative boundary condition. There's effectively no restriction on these solutions so far. We have something similar to what we had for the free particle. there were no boundaries that were terribly restrictive. We did not end up with a quantization condition. We did not end up with enough of a restriction on our solutions that we ended up with something straight normalizable. But we have our two equations now involving a, b, f, and g. That, unfortunately, is two equations to go with four unknowns. We have our definitions of psi in terms of a, b, f, and g, and these e to the I kx, e to the I minus kx, e to the minus I kx. And then we have our two equations relating a and b and f and g. It seems like we're not going to be able to come up with a very rigorous solution here. But we can actually do a little better if we start thinking about what the initial conditions might actually be. First of all, note that these solutions are the spatial part, and if we add a temporal part to come up with an overall solution for an overall wave function, we'll end up with the same sort of traveling wave states that we had for the free particle. The time dependence for those states was essentially e to the minus I e t over h bar. If you look at each of these terms, you can see this is a plus I kx going with the minus I e t. As time increases, space must increase here in order to maintain a constant phase. So, as in our discussion of traveling waves, the plus I kx here for positive values of k is associated with the wave propagating to the right. So if you think about our boundary here at x equals 0, in the space to the left of the boundary, where we're considering psi 1, we have a wave coming in from the left, whose amplitude is given by a. Conversely, the term with b in it here is associated with e to the minus I kx. That represents a wave traveling away from our boundary with amplitude b. Likewise, in region 2, where we have f and g, we have a wave f traveling away from the boundary and a wave g traveling towards the boundary. Considering the initial conditions now, we have waves going towards and away from the boundary on both sides. If the initial conditions I am interested in are, for instance, our initial conditions are, say, scattering from the left, what we're interested in then is waves incident from the left. If you imagine waves coming in from the left, you may have some waves going out to the left by scattering waves off of your boundary. We may also have some transmitted waves propagating off to the right, but we will not have any waves incident from the right. What that means is that if we're interested in waves scattering from the left, we can say g is equal to 0. This is not a requirement. This is just a sort of useful restriction on our solution to allow us to interpret what we're looking at in a little more detail. The second key fact now is if we're looking at scattering from the left, A is effectively our incident wave. If you think about the physicist as an active part of this system, shooting waves in from the left, A is effectively an input. So we don't necessarily care about the value of A itself. It's something that we set. You could say set A equal to 1, if you wanted, in a suitable experiment. So G is 0, and A is our incident wave. As such, going back to these equations, we can cross G out, because G is equal to 0, and we can look for things in terms of A. We don't necessarily need to know A. We can find, for instance, F in terms of A, and B in terms of A, by appropriate manipulation of these equations. That will tell us what F is and what B is in terms of A, which is something that we set. So that's all right. Instead of having 4 unknowns, if we set G equal to 0, we have 3 unknowns. And if we say I as an experimenter am setting A, then I know A. So I really only have 2 unknowns, F and B. And if you go through that exercise and solve for F and B, what you end up with is B is equal to I beta over 1 minus I beta A, and F is equal to 1 over 1 minus I beta A. So this tells us what B is in terms of A and what F is in terms of A. That's pretty good. What I'm getting at now is if I send a wave in from the left, that's represented by amplitude A, I can calculate an amplitude B on the basis of amplitude A. Really what I'm interested in is the ratio of the amplitude squared of B and the amplitude squared of A, because that's telling me about the probability amplitude of the left-going scattered wave. Something incident from the left scatters back to the left, a reflection event. Whereas F, if I look at the squared amplitude of F, that's the probability magnitude of a wave propagating through the barrier. I send a wave in from the left, and it propagates through the barrier. This is a transmission event. So if I look at reflection and transmission in terms of my definitions, or in terms of my solutions for B in terms of A, or F in terms of A, you can think about the probability of reflection, R, being defined as the squared magnitude of B divided by the squared magnitude of A. If I send more A in, I should get more B out. These things have an exact ratio, and really this number is what's most important. And if you look at that, you can calculate that out pretty easily. It's beta squared over 1 plus beta squared. That's called our reflection coefficient. Our transmission coefficient T, being defined by the squared magnitude of F over the squared magnitude of A, again, looks very similar to B, except we have 1 over 1 plus beta squared for the transmission coefficient. So these are our definitions of reflection and transmission coefficient in terms of ratios of probability amplitudes. If I send an amplitude A in, I'll get what is the probability, what is the fraction of particles that are going to scatter back, essentially, as represented by a ratio. If I express these in terms of the definitions of beta and k, which, if you recall, beta was defined to be ma over h bar squared k, and k was defined to be square root of 2me over h bar, what we end up with for our reflection coefficient is 1 over 1 plus 2 h bar squared e over ma squared. And for our transmission coefficient, we get 1 over 1 plus ma squared over 2 h bar squared e. So, looking at these two expressions, you can easily see that if I add the reflection coefficient and the transmission coefficient together, r plus t, I get 1. This is good. And if you look at my reflection and transmission coefficients in terms of the energy, if the energy increases here, the denominator overall increases, and our reflection coefficient gets smaller. So for higher energy incident waves, the reflection coefficient decreases. That makes sense. The more energy you have when you're approaching a barrier, the more likely you are to penetrate the barrier. The transmission coefficient, by contrast, has the energy in the denominator now. So if energy increases, this quantity decreases, the overall denominator gets closer to 1, and the transmission coefficient gets closer to 1. As is required by the sum of reflection plus transmission probabilities is equal to 1. So that is more or less the gist. This is the key result of looking at scattering in the context of a delta function, in this case a delta function well. You can calculate quantities called the reflection and transmission coefficients purely from quantum mechanical considerations that tells you how much of the wave will reflect back and how much of the wave will be transmitted. For instance, if I had some wave packet, when I construct a wave packet, I'll have a spread in energies, but I can look at these reflection and transmission coefficients essentially averaged over the range of energies that I need to construct my wave packet as the effective probability that that wave packet will be reflected back or transmitted through. One final note now. If we have a delta function barrier, my reflection and transmission coefficients actually don't change. The delta function barrier, instead of a delta function well, means I'm going to be looking at something like this instead of something like this. Or these now are infinitely narrow delta function distributions. how I defined things originally here was that v of x was equal to minus a times delta of x. So essentially, my barrier now is just a negative value of a. A is less than 0. And if I swap the sign on a squared doesn't change. So my reflection and transmission coefficients remain unchanged. That's very interesting. What we would have had classically is that if a is greater than 0, we have a well, we would have had transmission coefficient equal to 1 and reflection coefficient equal to 0. This is your cart rolling on a track that has a dip in it. Your cart rolls down the well, picks up speed, rolls up the well, loses speed, and then leaves with exactly the same speed as it entered. It certainly would never be reflected back, certainly not only some probabilistic fraction of the time. If I have a less than 0, I have a barrier. In classical physics, that would mean I have transmission coefficient equal to 0 and reflection coefficient equal to 1. This is what happens when you have your cart rolling up towards a hill, except it doesn't have enough energy to go over the top of the hill. In this case, since we're talking about a delta function, the hill is infinitely high. It's also infinitely narrow, but that doesn't matter from the classical perspective. The cart will roll up the hill the amount it needs to in order to run out of kinetic energy, at which point it will stop, turn around, and roll back. You'll have no transmission and 100% reflection. Quantum mechanically, we get the same thing. Whether we have a well or a barrier, the reflection and transmission coefficients are unchanged. This is an example of what I mentioned earlier as quantum tunneling. Quantum tunneling, where the particle penetrates a barrier that it does not have enough energy to clear, is an especially easy thing to calculate in the context of a delta function like this. But really, this is kind of a remarkable result. One way in which quantum tunneling like this is used, and I have a very small space here to attempt to explain this, is in quantum tunneling microscopy. What that means is you have your substrate, in this case, say it's a bunch of silicon atoms on a wafer. Quantum tunneling microscopy involves taking an electrode, a very sharp electrode itself, made of atoms, say it's only a single atom sharp, and looking at the rate at which particles are able to jump from the surface, the substrate, to your electrode. The electrode is not actually touching the surface, so we can look at this as having, say, as a function of height, let's look at, say, v of z now. You have a relatively low potential energy for electrons being in your electrode, a very high potential energy for electrons being in the free space between your electrode and the surface, and then again a low potential energy for the electrons being in the surface. And we'll look at this in the context of the next potential that we'll be considering, the finite square well potential. You can calculate the probability of a particle tunneling, jumping from the surface to your electrode, and it turns out the current of, if you're looking at electrons, jumping from the surface to your electrode is very sensitive to the distance that the electrode is from the surface, which allows you to make a very sensitive measurement of the height of the surface. And if you look up scanning tunneling microscopy, you can actually get images of the individual atoms on the surface, subatomic resolution, with a microscope, which is really pretty cool. To check your understanding, here are two questions to interpret what actually happens in the case of scattering states for the delta function potential. Is a potential v of x given in terms of a Dirac delta function. A now is just a constant that defines how strong the delta function actually is. So our potential is everywhere 0, except at some point where it goes to negative infinity. This is a plot now of v of x as a function of x. What we discussed in the last lecture was the bound state solution. What happens if we have an energy E of our state that's less than the potential, less than 0, less than the potential away from the delta function? And what we got was a wave function psi of x that looked something like this. Going down towards 0, away from the actual position of the delta function. I haven't done a very good job drawing this, but I think you get the idea. The scattering state solutions, by contrast, have energy greater than 0. So we're talking about solutions with energy E up here. At regions away from the delta function, we have basically the behavior of a free particle. We get traveling waves at regions away from the delta function, away from x equals 0. We don't really know what happens at the origin, but we know what our solutions should look like, and we should be able to use our boundary condition matching to figure out what happens at the origin. So what do our scattering states look like? Well, away from x equals 0, we have v of x is equal to 0. That means our Schrodinger equation, the time-independent Schrodinger equation, looks like minus h bar squared over 2m times the second derivative of psi with respect. We've developed the machinery to solve the time-independent Schrodinger equation for the delta function potential by connecting solutions covering the regions away from the delta function and matching them together with boundary conditions at the delta function itself. The last lecture discussed the bound state solution. This lecture discusses the scattering state solutions. To put this in context, what we're talking about